Thank you for joining me this afternoon. These lights are really difficult to see who is in the audience. I'm going to give you a different presentation, at least from the one that I heard earlier today, so I apologize in advance if it's not according to expectation. So what I will start with is actually with an email that I just received less than 2 weeks ago from Intel. And to give you a feeling of who we are and what we do, so even though we are in academia, and I have been in academia for way too long, we have created something that people are using to do definitely real science and beyond. So here we have a request from Intel that basically saying, can we use your logo because we have a reference architecture for some genomics and we would like to use it. And sure they did. And I must tell you that if I look around, who else is in this logo collection, it feels pretty good. So what I'm going to talk to you about is about the thing called HTCondor, where HT stands for high throughput. But before I tell you how wonderful we are and why you should go home immediately after this talk and start using it because it will transform your life, let me share with you some of the wisdom that has been guiding me, at least, in my work. So I like to start with Kohelet and to tell you that what guides me in my work is that there is really nothing new under the sun. And even though we are hearing here about this is wonderful and this is great and this is transformative and and the hype terms are flying left and right and up and down, I will try to convince you that in many aspects with big data or data science, we are actually going back to basics. And that there's really nothing new under the sun. The problems are still very hard, but there's nothing new about them. And to create some context here, I like to share with my audience, don't forget I'm a professor, a paper that Enslow wrote in the late 70s. And yes, we had the computer science journals in the 70s, where he listed the benefits of a distributed system. And what is really wonderful is that after taking a detour to the parallel MPI world, we are going back now to the distributed system that we had in the 70s. And here's a list of all the wonderful things the distributed system can do for you. And by the way, I didn't hear that much about real distributed computing, at least in the presentation that I attended. Now, delivering this is very difficult. And that's the reason why we are still struggling with it. Now, to frame more what I'm going to talk about is I will use a paper that I published as part of my PhD work at the Weizmann Institute in '82 about load balancing in distributed systems. And I heard here earlier we'll do load balancing, we will move things around, everything is easier said than done. And the conclusion of that paper that was published in '82 was that really what we should try and do is minimize what I refer to as the wait while idle state, namely that there is a request to do something waiting in one place and that there is a resource that's willing and capable to serve sitting unused or used by a lower priority task on the other side. And you can mathematically show that the probability of this state is pretty high as you have a relatively small number resources in the system, much, much, much smaller than what we have today. And I will give you some numbers as we progress. So I took you to Kohelet, which is 2,000 years ago. I took you to Enslow and my PhD work that is 40 years. And I will give you some other events. Actually, I will talk to you later about an event that happened 1.3 billion years ago, speaking about time and data. But if you take the idea of wait while idle that you want to eliminate, then you really must adopt the principle of submit locally and run globally. You want to be able to do, whether it's your Spark or your MapReduce or your whatever is the next great thing that you are going to do your data analysis, you want to be able to say, hey, do it, use my local resources, but go out there to any place around the world and find resources for me. And I know that today this sounds pretty natural when you start thinking about the commercial clouds that are out there, and everyone tells you, go out there and run. And it's sort of a little bit ironic because this meeting is organized by what was the grid technology group here that added cloud to it. But Ian Foster, who is considered to be the father of the grid, quotes me saying that we did clouds before they were called grids. Because the idea of going out from your local environment and running in the global environment has been always a principle that we believed in, and it was a natural consequence of the desire to minimize the wait while idle state. So we deployed the software that I'm going to talk to you about for the first time in production in 1985. At the time, it was 20 deck stations. Today, we have to manage a night landing that has more cores than our entire system in 85, and I will give you some numbers of what we are managing today. So that's as far as we are going back. And 20 years ago, I coined the term high-throughput computing to differentiate what we are doing from what everyone else has been doing around us, and that they labeled it as high-performance computing. And the way that I like to differentiate between high-throughput and high-performance is that, A, we don't care about what we can do in a second, like any high-performance system that can do that many petaflops or teraflops, or now that we are talking about exaflops. But we care about what we can do in a year, and what you can do in a year is not what you can do in a second times the number of seconds in a year. The other element of high throughput is that you are dealing with many, many, many jobs or tasks or whatever you want to call it. And if you're looking at some of the new framework for doing machine learning, then you have these graphs or the directed acyclic graphs that allow you to express the execution of what you are doing, the pipeline, as many things that you need to manage. And I'll give you some numbers about the sizes of DAGs that we are managing in support of science. So it is about having a lot of jobs, a lot of users, a lot of sites, a lot of servers, and we at least have workflows that can run for days and weeks. And I know that there are needs of high-rate trading and stuff like that is really real time, but we talk a lot about training and tuning and simulating and understanding, and at least what we have learned in our science world, these things take days, weeks, and months to accomplish, and can consume huge amount of computing resources. So in Condor, we have a unique approach where we use matchmaking to acquire resources, and then we use matchmaking to provision the resources that we acquired to the queued jobs, and then we launch the job. So we really separate between these three steps. And if you think for a moment, and I saw the word batch showing up in some of the slides earlier today, the key element of batch processing is the provision of resources. You can do things very fast once the resource is yours. But if the resource is not sitting there and waiting for you to use it, then you have to go through a non-trivial delay in getting it. It can be a minute, it can be an hour, it can be a day, it can be a year. So think about batch more as a way to acquire resources than a way to run them. Launching the job is the simple step in batch processing. So this is sort of a schematic picture of how we consider the overall elements of a batch system. And as you can see there, there is an acquisition manager that goes to a marketplace and say, where can I get more resources? I have all this stuff that I need to do. Where can I get more resources? Not just the resource that I have at the moment that I can provision, but where can I get more? And you know, clouds are a beautiful example of the elasticity that a system like this can benefit for and deliver it to the end user. So a quick list of the things that Condor can do, and then I will take you to the examples of the kind of application that can run under Condor. So you submit it to something that we call the SCED. This is the agent that is taking the work from you. And what you are submitting is an executable. It can be a container, it can be a virtual machine. Really, a virtual machine and a container is an executable in a different form. And if you keep in mind what I told you earlier, that really when you submit a request, you are basically submitting an acquisition request. Now you see why it is so flexible, because when you ask for a container, you're basically saying, can you find for me a resource that can run this container? And then the SCED can do matchmaking with different marketplaces. So it can really expand to bring resources or to acquire resources from many, many places. And I will give you some numbers and scales in a moment. And then the SCED can take a task and delegate it to a resource that it acquired. But it can also talk to other batch systems. It can also talk to other grid systems, and it can also talk to various cloud systems, because at some level, a cloud system is not different than a batch system, because when you go to a cloud system, all you are doing is you're coming and saying, can you provision for me this kind of a resource? Either now or in the future if you're going to spot and the price is right. So you see that if you follow this abstraction, batch system, clouds, grids all look the same because they basically do for you provisioning. So one of the examples where our technology is being used is something that's called the Open Science Grid in the US, which is a high-throughput computing facility that is spread across over 60 sites and has over 100 clusters at the different sites. And it's a consortium that has been running for over 10 years now. And just to give you numbers, this is sort of a map of the sites. but what really matters here is the numbers. So last year, we delivered 1.4 billion core hours, and we moved 165 petabytes of data in the Open Science Grid. So that's what we do as we speak. In the last 24 hours, it was only 3 million hours and just half a petabyte. So this is what this open source, free, available technology can do on a daily basis. And it implements this submit locally and run globally because the user is sitting there, it has this entry point, and Open Science Grid can take it to all of these different types of resources. And we even get Nobel Prizes or mentioned around Nobel Prizes because the Higgs boson or the God particle that was detected at CERN, this is an event that is only 40 years old because the prediction of the existence of the Higgs boson was made 40 years before it was discovered. Now, you may find it interesting that the National Academy of Science recently in the US had a report where it recognized that high-throughput computing is becoming critical to scientific discovery. So if you think about the work that you are doing in data science, right, we have the word science there, then I strongly encourage you to take high-throughput computing seriously because, as I will show you in some of the examples later of how it's being used in science, it's extremely powerful, and machine learning is an integral part of it, but it's not the entire story, because you need simulation and you need to do data acquisition, and you want to do it all in one framework because all of this is consuming significant computing resources. So to give you a feeling for scale, here's a presentation from the Google Grid group that took place in our annual meeting that was earlier this month in Madison. And what I found here interesting when he listed the agenda, he crossed out the big on data. Because I agree that the problem is data, not big data. We always had data, and data is the problem, and we don't know how to deal with data, or we don't know how to deal with storage. That's a different talk, but it's not big. But what I wanted to show you here is a demonstration that we had at the Google booth at Supercomputing 2016, where we produced 150 terabyte of simulated data for the CMS experiment. But what is impressive, this is the number of jobs that were running through this week by the CMS experiment, and the scale is 350,000. And the top there were cores that we got out of Google Compute Engine. So, and all of this was managed by HTCondor. So we were running at the level of 350,000 concurrent jobs. Doing simulation, for me, it is data science. Generating data that was used to study a phenomenon. And underneath this was something that is called HepCloud, which is a project coming out from Fermi, which again has this idea, and all of these are Condor pools that are running and submit locally and run globally. At the University of Wisconsin, we have a Center for High Throughput Computing, and here are the numbers of hours that we delivered over the last 3 years. We are now close to 375 million hours in 12 months, and we have served 205 projects. And let me give you a feeling for what kind of project high-throughput computing can support. So one example is David Page, high throughput machine learning. That's again from our meeting earlier this month. I just picked up some of these slides to give you a feeling. I'm obviously not an expert in any of this. Supported by NIH, doing phenotyping. Here's a graph of the predictive power of the models that they have developed using machine learning. And by the way, I'll be happy if you contact me to either give you more information about any of these topics or connect you to the expert, because I'm just the middleman. And here's a list of, according to David, on what the challenges are and why using the high throughput computing capability that we made available to him. I think this graph took 125 years of computing in order to develop these predictive models for ER records. Another example is work that I asked Tony Gitter about his work that he's doing in using machine learning for drug discovery, and why is he using. Now, David didn't use GPUs. Tony is also using GPUs as part of his machine learning. And here's an explanation in his terminology of the challenges of doing learning and machine learning in the context of drug discovery, given the number of chemicals that they have and the few numbers of positive cases that they have to deal with. And he's still in early stages and is planning to expand into the elasticity of clouds and GPUs there soon through the Center for High Throughput Computing. Another example is statistical modeling of satellites images. And here we have an example of an environment in Python. And here the information is images. And again, data processing, feature extraction, coming up with a pipeline, thanking us for everything that we did for them. Another example of big data is for Alzheimer's studies, MRI analysis, more of the same. Another case, this is a collaboration between the University of Wisconsin and people at the Texas Health Science Center. First of all, simulating it, then analyzing it. And just as a small hint, Condor is not used only for these kind of activities. So here's a report from Raytheon in our meeting earlier this month about their usage of HTCondor. So it's not just in academia. Here's another example for cycle computing, for electronic design automation. Again, the same story, simulation, data analysis, a lot of high-throughput computing applications. I promised to take you back 1.3 billion years ago, and that's what the LIGO experiment did. They detected an event that happened 1.3 billion years ago that created gravitational waves that have proven that Einstein was right about his theory about gravity. And I will let you think about what it means to have an event that happened 1.3 billion years ago. And they have been using HTCondor for 15 years. They have been using our workflow system that's called Dagman, and they have 600,000 jobs in a single workflow. And the idea behind it is that they can create, this is the in-spiral, a piece of it. It's not a simple fork join. There is a lot of data exchange. We saw a little bit of it earlier today in some of the presentation about the flow of the data in the machine learning that they have to conduct, and that running these 600,000 jobs may take several weeks. So going all the way back, in the late 80s, there was something called the parallel virtual machine, which was a very nice distributed computing environment that was killed by MPI. And PVM had the ability not only to do message passing, but also had resource management primitives. And we worked on it, and we were very happy, and it was very useful until it was killed by MPI. What is so wonderful now that systems like Dask, that we start working with it recently, and I think there will be another talk about Dask later today, are bringing us back. I think the Dask is still primitive compared in resource management compared to what PVM did. And at the time, we created something which was the Condor resource management interface that we called CARMI. And we hope to get back to it because maybe now the time is ripe. My concern, from my perspective, is there are now so many different environments, you never know which one will actually be adopted as a real system. So going back to Kohelet, what I want to tell you is that the principles haven't changed. The challenges haven't changed. What is changing is the scale, not only of the application, but who is using it. And I think this is the biggest challenge of how to bring these tools into the hands of people who are not professionals in computing. And I'm not sure that what I see is very promising, because I am old enough to know that there was parallel or high-performance Fortran, where people were told, don't worry, you write Fortran, and we will turn it into a high-performance application that will run beautifully on any machine. It didn't work. And what I hear today is similar to it. So it is out there. You're welcome to try it. Feel free to get in touch with me. And good luck with all the data that you have to deal with.